Hi everyone, welcome to my video on control systems. Today I'll be giving an introduction on frequency domain analysis. Let's consider a system GS, which is our plant, and input as well as output. Previously, we have been considering input of unit step input, whereby it is just a one straight line, and we result in an output of probably first order, second order under them, or second order over them response. Those are time domain analysis. In this chapter, we are going to look at frequency domain analysis, whereby our input will be in a different form, which is a sine wave. And we are looking at LTI system because of the linearity properties. When the input is sine wave, the output will be also sine wave and will be at the same frequencies. As you may observe here, when the input and output are both sine waves with the same frequencies, only two things can possibly change. The first one is the magnitude, which is the difference between the amplitude of the input and output. The next one will be the phase shift. It's a phase difference between the output and input. And we may also say that these changes are also being brought by the change in the nature of the transfer function that responds to the change in frequencies. So in the frequency domain analysis, basically we are looking at how do we analyze the change in all the earlier said properties. So there are few ways of doing it, and the most common one will be the Bode plot. The figure here shows a Bode plot, which you can see here are divided into two sections, and also it is in the range of semi-log. The upper one is the magnitude, which is 20 log base 10, the ratio of the output amplitude over the input amplitude, which basically an indication on how the system output grow or shrink when the frequency changes. The idea is we start with a small frequencies, we record the magnitude difference between the input and output, and we do it over and over again, and this is how we get the magnitude plot. Okay, so we have done with the magnitude plot. The next one will be our phase shift. Basically, phase shift, we are trying to find a phase difference in degree between the input and output. To get the phase shift of two waveform, we can find out what is the time difference between two signals when they cross zero, and we convert it to degree. So as you can see from here, basically the idea of getting the phase shift is very similar to the idea of getting the magnitude plot. The magnitude plot and the phase shift plot combined together will constitute our Bode plot. In the later modules, we are going to learn how do we sketch the Bode plot by hand and then use it to find out the stability margins, and also we can use Bode plot to design our lead lag controller. Okay, next we move on to the Nyquist plot. Nyquist plot is different from Bode plot, whereby Nyquist plot looks into how the system changes in response to a change in frequencies. We will consider our GS, which we are going to convert to GJ omega. The GJ omega will then be broken into this real part and imaginary part in terms of frequency. And Nyquist plot is basically the imaginary of G omega versus real of G omega with varying frequencies. As you can see from here, the Nyquist plot is basically a contour of real and imaginary of G omega with angular frequency starting from negative infinity to positive infinity. We'll be using Nyquist plot primarily to determine the stability of the system. Here is a simple illustration on the difference between a Bode plot and also Nyquist plot. The Bode plot depicts the relation between input and output over varying frequencies, while the Nyquist plot depicts the change in the nature of the system correspond to change in frequencies. Okay, that's all that I want to share in this video. Thank you very much for watching. Bye.